video, we're going to explore some problems that involve proportional reasoning and similar figures. And this is going to lead into where we're going to be going in lesson number 2, which is some of our unit conversion. So proportional reasoning is the process of basically maintaining equivalence. So for example, if I have something like a relationship that's like 2 feet by 7 feet, that's going to be proportional to an object that's 6 feet by 21 feet. Because basically, I would get from one relationship to the other by simply multiplying by a scale factor of 3. So it's sort of, if I times both of those numbers by 3, I'd wind up with my new numbers. And, I could say these are both proportional to 3 feet by 10.5 feet. In this case, I went and I times each of my numbers by a factor of 1/2. And all 3 of these fractions are what we would call proportional to each other. Now, when we look at it within figures and we talk about maintaining that proportionality, we're looking at sort of taking an object and they're going to you're maintaining, the same shape, but a different size. So all of the side lengths within the figure were multiplied by the same value, or all of the side lengths in the figure were divided by the same value. And sort of the key with these relationships is that multiplication, that factor that we multiplied by. And you'll hear that often referred to as the scale factor. Now we're going to start with a situation that maybe most of us might be familiar with, a photo. So here's a photo of my family. And if I went and just downloaded this photo from my computer, it would actually come out huge. It comes out 18 inches by 24 inches. Now, let's be honest, no one wants a photo that big. Maybe for a special case, but that would be huge. That's over 2 feet tall. So normally when you get photos printed, they're actually getting shrunk down from their digital size, but we maintain proportionality. We're not going to elongate anyone's faces. We're going to keep that relationship, that 18 inches to 24 inch relationship, constant no matter what size we make the photo. And so we're going to do 3 things to this photo. First, we're going to shrink it to half the size. Then we're going to make it poster size. And then we're going to try and fit it into a frame. And what would the side lengths have to be? So let's start with that first problem. So we want to shrink the photo to half its size. And as I said, we want to maintain that 18 inches to 24 inches relationship. But basically in our new photo, everything's going to be half the size. And so that means we're going to be basically multiplying each of our side lengths by a half. So 18 inches by a half would mean the new photo is 9 inches wide. And instead of 24 inches tall, it'd only be 12 inches. So now it's only a foot high. Probably still a little on the large size, but it's smaller. And the point is that the dimensions stayed the same. It's still a rectangle. It's just each of those dimensions got a little smaller. So it went from being, 24 by 18 to 9 by 12. So we shrunk it down. Now, we can do this sort of same reasoning, but we can make it get bigger. So I'd start with that 18 inches by 24 inches, but this time we want to triple it in size. So if I multiply all my dimensions by 3, then my new photo will be 3 times as big. And so I'd end up with 54 inches by 72 inches. And so in both of these cases, we didn't have a fixed side length. We were just saying, okay, we're going to make it bigger, we're going to make it smaller. Now, in part C, though, we're a little different. This time, we still have that 18 by 24, but we're told that that long side isn't just any old number. I'm not told what I'm shrinking it by. I'm told I need to fit it in a picture frame that's 7 inches tall. And so what would that other side length need to be to keep this proportional? So like, what would I multiply 24 by to get to 7? And that's not necessarily like the easiest math problem to think about. And so to approach problems like this, sometimes we set up what are known as proportions. And so it's this idea of saying, okay, we have that 18 to 24 relationship, and we want to make that equal to some unknown side length, I don't know what it is yet, to 7. And you know, if I can't quickly see what I need to multiply by to get to 7, well, a fraction is just a division problem. So if I multiplied both sides of my fraction by 7, both sides of my equation by 7, the 7's here would cancel, and I would basically be left with whatever I need for x, which would be 7 times 18 over 24, which comes out to 5.25 inches. So that's one way to approach it. That would allow me to sort of figure out that unknown side length. Let's look at a similar idea to that part C, but within a different shape. So if we look down here, you'll notice we have, and I'm going to move these down a little so we have some more space. We have 2 triangles, and these triangles are similar, meaning they're the same shape, like all of their angles would be congruent. And I'm going to switch back to my drawing mode. Like the corresponding angles would be congruent, but the side lengths aren't. This second triangle is clearly smaller than the first triangle. So we would refer to these as similar triangles. And in similar triangles, the side lengths are proportional. So there is a number that I could multiply 9 by and wind up with 6. But let's approach this. We want to find the length of A in the big triangle and C in the small triangle, just like we approached that photo problem. So to start with, we're going to look at B and C. And the reason I'm choosing B is because I know the length of B in both triangles. And so I want to know what C is in this small triangle. I know C in the big triangle. It's 12. And in this, the relationship between B and C would need to be 12 to 9. And then in my other triangle, C is unknown and 6. So it's like I've set it up so that my C's are both on the tops of my fractions and my B values are both on the bottom. And just like with that previous problem, we want to get C by itself. And I can't clearly see what I'd multiply 6 by to get to 9. Maybe you could notice that it would be 3/2, but maybe you don't. And so I can, just like the last one, multiply by 6. And so I'd get 6 times 12 divided by 9, which would come out to the fact that C would need to equal 8. And you could check this. So 12 ninths reduces, 3 goes into both of them, to 4 thirds. And if I check 8 over 9, also reduces to 4 thirds. And so my fractions are equivalent. And that's what it means to be proportional. We're going to find A using a slightly different method. To find C, we set it up side lengths, sort of proportions within the same triangle. This time, I'm going to set up my proportions so it's like I'm comparing side A to side A and side B to side B. And so what happens here is I'd say A to 4, which is my A in my other triangle, should be equivalent to whatever 9 to 6 is. And in this case, again, I don't necessarily have a clear number I'd multiply 6 by to get to 4, so I could multiply both sides of my equation by 4. and I'd end up with A equals 36/6, which is just 6. And I can double check my answer. 6 over 4 comes out to 3/2, and 9 over 6 comes out to 3/2. So check, my answer works. They're proportional. We have maintained our equivalence. Notice also, just sort of a tip as I'm setting up my proportions, you should notice that I put my variables that I'm looking for on the tops of my proportions. It makes the equation and the manipulation a lot easier to do, and I would strongly recommend doing that in the future. Hopefully this helps you sort of introduce some notions of proportionality. We're going to keep using this throughout the semester as we do some other types of application problems, and hopefully by the end we sort of have a clear understanding.